Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our thermodynamic lectures. Today, we want to look at heat transfer from a vertical wall. From a vertical wall. When you have this vertical wall which is in contact with some stationary fluid, if the temperature, the wall is high, then the fluid will move upwards. But if the temperature is low, the fluid will move downwards. So if the temperature the wall is high, the fluid will move upwards, move downwards if it is low. Now, these movements, therefore, of this particular fluid will be the result of temperature gradients. And these temperature gradients, of course, result in density gradients. You have already seen when we are talking about turbulent layers and so forth, or turbulent processes, we saw that there were development of eddies based on density gradients and velocity gradients within the system. So this disrupts the system. So these temperature gradients will lead to density gradients, and this, of course, will result in fluid motion. So the fluid motion is due to the temperature gradient which results in density gradients. So basically, when you're talking of these fluid motions, you will basically find, because of this explanation which you have given here, that the movement is basically as a result of complementarity between viscous flow, viscous forces, and buoyancy forces. So inertial forces are not very significant. Remember, we talked about inertia when you're talking about the turbulent processes. When you're talking about turbulent processes, we talked of mass transfers and rate of momentum change, which the rate of momentum, which is basically the shear stress. So in this particular case, these fluid motions is basically a competition, or is complementary between free convection and buoyancy forces. So the fluid flow is the result of complementary force activities involving buoyancy and free convection. Free convectional forces. Buoyancy and free convectional forces. And so basically what we have said, inertia does not play inertial forces don't play much role. Now, suppose we focus on some volume element, and this volume element is at a higher temperature than the surrounding fluid. So if you consider volume element, let us say we have that volume element there, and we have the surrounding fluid. Let's say that the temperature of this volume element is TE, and that of the surrounding fluid is TS. So we are saying TE, temperature of volume element. Let's call that volume element dV. And the temperature of the surrounding solution liquid, TS. So if the temperature of the volume element is higher than that of the surrounding liquid, then the density in the volume element will be lower than that in the surrounding liquid. So if the temperature in the volume element is greater than the temperature in the surrounding liquid, then the density of the volume element will be greater than that of the surrounding. Or the volume element will be greater than that of the surroundings. And so we have talked of buoyancy. So the velocity of this volume element will be the result of buoyancy forces. What is buoyancy? We have used that word. Let's just take focus on it a bit. Let's just note what we call the Archimedes principle. And in the Archimedes principle, it says that the buoyant forces pushing upwards is equal. The buoyancy forces pushing upwards is equal to the weight of the fluid displaced by the immersed object. The buoyancy forces pushing upwards is equal to the weight of the fluid displaced by the immersed object. And so the buoyancy force can be represented as that, where that is density, volume, and this acceleration, which you're familiar with. And so the movement of this volume element in the fluid is as a result of the buoyancy forces, which we can represent as follows. So the movement of the volume element is the result of buoyancy forces. And remember, we said that because the temperature of the volume element is higher than that of the surrounding fluid, then its density is less than that of the surrounding fluid. And so remember, the density of the volume element is given by that fraction there. And this beta here is the coefficient of cubical expansion. The coefficient of cubical expansion. What is that? What does that mean? In simple terms, we have the unit volume. So when you raise the temperature by unit amount, that increase in the volume, is what we refer to as the coefficient of cubical expansion. It is that increase in the volume of the original unit cube per unit rise in temperature. And we have said that that movement of this volume element It's more so because of buoyancy forces. And that movement, the velocity, of the unit element, unit volume, due to buoyancy forces, can represent that as rho. That will be theta. So we expect that this quantity here should appear somewhere in our expressions, in our final expressions, when we are talking of the rate of heat transfer. The rate of heat transfer. All of these quantities have their usual meaning, which you are now very familiar with, and I continue encouraging you and urging you, humbly requesting you to go through all our lectures systematically so that you build up together. Build up together as we move on. Now, if we look at a schematic of what happens in these heat transfers from the vertical wall, remember we have already seen that we always have a buildup of velocity boundary layer and thermal or temperature boundary layer. And that is when we are talking about laminar flow. So we are going to consider laminar flow. Okay? What we are going to deal with here is laminar flow. That's involving the vertical wall. We are not looking at turbulent flow. We're looking at the laminar flow. So we can have a schematic of heat transfer from the vertical wall. On the vertical wall. Like I've said, always remember, we are now familiar with thermal boundary layers. We are now familiar with velocity boundary layer. And you remember, when we were talking about laminar flow, remember we saw that this quantity, which was the ratio of the boundary thicknesses for the velocity boundary layer and the thermal boundary layer, this quantity we said was 1 over Prandtl's number. That's the cube root of Prandtl's number. And remember, Prandtl's number we said was the dynamic viscosity times Cp over thermoconductivity. And so we say that when this Prandtl number was 1, then when Prandtl number was 1, then this boundary thicknesses for the velocity and the thermal boundary thickness or temperature boundary thickness were the same. So don't forget that. This we said was for laminar flow. Don't forget that. Now, so when we draw the schematic, we'll have our wall. That's our vertical wall. That's Y. We call this X. This is our vertical wall. It's our vertical wall. So we have our vertical wall, X and Y. And so, what do we have here? So that if the temperature at the wall, let's call that temperature at the wall TW, the temperature will decrease until it is Ts at that particular point. So the temperature TW will decrease to Ts. That's the temperature at the wall, that's the temperature in the solution. And in terms of velocity, the velocity profile, when you're talking about the velocity profile, it will be 0 at the wall. Don't forget, we talk of the no slip condition. It will be 0 at the wall. We expect it to be a maximum and then be 0. So this is velocity, this is temperature. U is velocity, and that is temperature. So we expect there to be some maxima. So we have this free convection velocity maximum. And then, of course, it will be 0 at the edge of the boundary, at the edge of the boundary. And at this edge, at this boundary here, we are saying that the thicknesses for the velocity and the thermal boundary layers are the same. We are saying that the thicknesses are the same. Now, for laminar flow, it's easy and it has been derived very easily. Remember, this x is the distance from the bottom, the top of the heated wall. That x is the distance. And so, what are we saying? There has been a relationship, empirical relationship, combination of empirical and theoretical derivations, which has been able to compute the thickness of the boundary layer. So from empirical, what is empirical? That means experimental data, and theoretical calculations. It is seen that sigma over x, where x is the distance from the bottom, to where we are marking our temperature, is found to be the Prandtl number multiplied by some constant, which is normally about 4, and the Prandtl number so this is a combination of theoretical and empirical data. It's a combination of theoretical and empirical data, this expression here. And it is found to hold. It is found to hold. So x is the distance from the bottom, the wall, so you can treat the bottom of the wall as a datum level or a reference level. You can treat it as a datum level or a reference level. And GR is the Grashof number. Grashof number is the Grashof number. And it's a combination of these quantities, so it's basically dimensionless. Basically dimensionless. Remember, we have seen several numbers. We have seen Prandtl number, Reynolds number, we have seen Stanton number, we have seen Nusselt number. Now this is Grashof number, which is also a combination of this quantity, so it's also dimensionless. So we have acceleration due to gravity, we have the coefficient of cubical expansion, we have the temperature, we have the density, we have that distance x from the bottom, that datum level, and we have the dynamic viscosity. This one just remind you that's dynamic viscosity, just in case you've forgotten. The rest are standard, we have already defined them. So, we have seen a profile of rate of heat transfer from a vertical wall. And we are still continuing with the derivations of these heat transfer equations involving the vertical wall. So let us stop at this particular point. We'll continue with the lectures.